So this is going to be a really long question, at least longer than what I usually do here on the channel. Um, this is still a rigid body dynamics problem, and it explores the idea of something called the center of percussion, which is this kind of concept that I think typically tennis players encounter, as well as baseball players. So essentially what happens is whenever you have your bat and you're using it to hit the ball, however the bat looks like. So when you hit the incoming ball with the bat, there is a certain position along the bat where if you hit the ball there, you don't actually feel the fact that you hit the ball, right? And that point, so that the point where you have to hit the ball for that to happen, is called the center of percussion. So this question explores the same concept, but it looks at it in a slightly different way. So rather than saying that at the center of percussion there's no shear force, because that's what happens, instead we're dealing with this chimney that's falling, and while it's falling, it may break, and if it does break, it will break at this point where the maximum bending moment occurs. And coincidentally, the place where the maximum bending moment occurs is the same place as the center of percussion, and this is what we actually have to show. Now, the way to do this is we're going to model this chimney as a long slender bar, which is going to be falling, and for a thin slender bar of uniform density, the location of the center of percussion is 1/3 of the way from the bottom, right? So the distance from the bottom to this point is L/3. So that's what we have to show. So we have to show that while this chimney is falling, the place where the bending moment is the greatest, has the maximum value, occurs at the center of percussion. So here's how I will go about doing this. First of all, I'm gonna model the chimney as a slender bar at a certain angle. So we're gonna say that this chimney started falling when it was in a vertical position, and now it's in this tilted position, right? So we're going to define an angle theta like this. And the question also says that there's no, or ignore any restraining moment at the base. So in that case, we can technically assume that this slender bar is hinged, right? So because if you have a hinge support, then there are no bending moments that will occur. So what I'll do here is I will first of all draw the free body diagram. So to look at the free body diagram, we have to add the forces. So we have two things, well, or three things depending on how you look at it. We have weight, so we've got mg, and we also have the reaction force, but actually the reaction force can be split up into a horizontal component, Rx, and a vertical component, Ry, like this. And that's all we have to work with at the moment. So what I'll first do is I'll write the equations of motion, right? So we can first write that Rx, which is the only force acting horizontally, is equal to the mass of the bar times the acceleration of the center of mass in the x direction. And then we have Ry minus mg is equal to the mass times the acceleration of the center of mass in the y direction. And then we can also use the moments. So in terms of moments, we have, well, let's take moments about this point O, and let's call this point here C. So if we take moments about O, the only force which produces a moment about O is the weight, right? So we have minus mg, because this produces a clockwise moment, and then you have multiplied by L/2. So I'm looking at this distance, right? And the perpendicular distance to mg is essentially L/2, and then we have cosine of theta. So minus mg L/2 cosine of theta. So that gives us this distance, and that is equal to the moment of inertia, which is, remember, you're taking it about this point O, so that's going to be 1/3 ml squared. You can find it from tables, or you can do the parallel axis theorem if you want, multiplied by the angular acceleration, which is theta double dot. Okay, so we can cancel out some stuff. We can cancel out the m's, we can cancel out an L, and we end up with minus g cos theta is equal to 2/3 L and then theta double dot. Or we can maybe say that cos theta is equal to minus 2/3 L over G theta double dot. We might actually change this in a bit. So it turns out that the rotation and the translation equations of motions are uncoupled, which means we can actually use only the equation of motion for rotation to solve for theta, basically. Theta is a function of time, if we want. So what I'll do here is treat this as a differential equation, right? So this is just an equation which has theta and theta double dot, right? Which is the second derivative of that. So I think what I will want is actually have theta double dot by itself. So I'm going to move everything around again. So this is going to be minus 3 over 2 and then g over L cosine of theta. Right, now technically we have to integrate twice, but what I'll do here is I will rewrite theta double dot in a slightly different way. So theta double dot is the same as theta dot d theta dot over d theta. Okay, so why is this the case? Well, because theta double dot is d theta dot over dt, and theta dot is d theta over dt. So if we eliminate time in both of those equations, we end up with this. So let's write that as follows. So we have theta dot d theta dot over d theta is minus 3 over 2, and then we have g over L cosine of theta. Now we can separate the variables. So we have theta dot d theta dot is equal to minus 3 over 2 and then g over L cosine of theta d theta. And then we integrate both sides. So we integrate like this, and we end up with, this is going to be theta dot squared over 2. And the right hand side is going to be minus 3g over 2L. And I think I put the minus. Yeah, and this is integral of cosine, which is sine of theta plus a constant. So now we have to find the constant of integration, which should be relatively easy. So we know that at theta equals, so when this bar was upright, in other words, when theta was pi over 2, theta dot was 0. So we can say that 0 is equal to minus 3g over 2L plus c, which means that c is 3g over 12. And that's it. So now we can go here and rearrange and find what theta dot or theta dot squared is. So we have theta dot squared over 2 is going to be equal to, so I'll write 3g over 12 first, because that's positive, and then 1 minus sine theta. So theta dot squared is going to be equal to 3g over L 1 minus sine theta. Right, so this is essentially the angular velocity as a function of angle. So what I'll then do is I will use this to find what the angular acceleration is. So if I differentiate both sides, so if I do essentially d by dt of both sides like this, what I'll get is on the left I should have 2 theta dot and then theta double dot using the chain rule, and on the right hand side we have 3g, we have 3g over L, and in the brackets we have 0, and then minus, we differentiate the sign, so we get cosine of theta times theta dot. So we have 2 theta dot times theta double dot is minus 3g over L times cosine of theta times theta dot. Theta dot cancels out, which is nice, because we just wanted theta double dot the acceleration just in terms of the angle. So this is minus 3g over 2l cosine of theta. Okay, that's it. So that's the angular acceleration, and this is the one we sometimes call as alpha. And theta dot squared, that was, just as a reminder, 3g over l, I think, 1 minus sine theta, right? And this is the same as, you're going to see me write this as omega squared. Okay, now let's try to use this to find what the question is actually asking us to do. So what I'll do next is I will take a section of this bar at a random position x away from the hinge. So let me actually do this here. So we have, so this is just this is the only part of the bar that we're going to investigate. So it's tilted at an angle theta, and then the hinge is somewhere here. So I'm basically separating, I'm not just separating the bar from the rest of the world, I'm separating a bar from the rest of the bar, essentially. So we've got a distance from here to here, which is, let's call it x, which means this here is L minus x. So if we separate this section of the bar, we have to add all the forces that are acting on it, right? So first of all, we have the weight, but this is just the weight. It's not the weight of the whole bar, it's the weight of this section, which, because the bar is homogeneous, this is m over L times L minus x times g. Okay, and then here where the section is, we have quite a few things going on. So first of all, we're going to have a force, which we're going to call it tension, right? Which I'll draw it this way, because why not? Other than that, we have another force, which is going to be like this. This is going to be the shear force, and we also have a bending moment, which I'm going to draw this way. And it's that bending moment that we're trying to extract, because that's the one that we're trying to maximize based on that distance x where we created that imaginary cut. So what we can do at this point is we can actually write the equations of motion just for this part of the bar. And to do that, I'm going to choose a coordinate system which is not going to be up and to the right. I'm going to choose a coordinate system and I'm going to place in the center of mass of this bar, and that coordinate system is going to be like this. So x goes along the bar, y goes perpendicular to the bar, which means that we will end up with two components of weight, right? So let's remember this angle here is what we called theta. This angle is theta, which means that we can find the components of this. Okay, so this component is going to be m over L, and then we have L minus x g, and then we should have that this angle should be equal to this angle. So this angle is the same, which means that this component is cosine theta, and then we have another component going this way, which is sine theta. So we have m over L, L minus xg sine theta. Okay, so we can start writing some stuff out. So in terms of the equations, first I'm going to look at what happens in the x direction. So in the x direction, I have two forces. I have the tension, that red force, which has to exist. And we also have this, so minus m over L, L minus x, g sine theta, and this is equal to the mass, but remember it's not just m, it's the mass of that section times the acceleration in the x direction. Now thankfully we won't have to use this equation at all, because we don't care about the tension force. Instead we will have to use the other two, which is the y direction as well as the equation regarding the rotation of the bar. So in the y direction, we have a few forces, namely we have two. So we have the shear force, which is S, which is in the positive y direction, and then we have minus this here. So actually, it should be minus this here. So m over L, and then we have L minus x, g cos theta. So those are all the forces, and this is equal to m over L, L minus x, multiplied by the acceleration of the bar in the y direction, and that's it. And then we look at rotation. So in terms of rotation, we're gonna take moments about the center of mass of this bar, right? So that's about this point here, which I'm gonna call this C. I called the previous center of the whole bar C, but this is, think of it as another C. So the moments about C are given by two things. So first of all, we have this bending moment M, right? So the bending moment is going to be actually minus M because I drew it as clockwise. And then this shear force S creates another clockwise moment, so that's going to be minus. And then we have S multiplied with the moment arm. Right, so the moment arm is the distance from C to this cut, which is L minus X over 2. So L minus X over 2, and that should be it. So those are all the moments acting about that C, because the tension doesn't produce a moment and the weight doesn't produce a moment. So this is going to equal the moment of inertia about the center of mass, which is 1 over 12, times the mass of the bar, which is m over L, L minus x, multiplied by the length of this section of the bar squared, so that's L minus x squared, multiplied by the angular acceleration, of course, so that's theta double dot, which now we have, we don't have a value for, but we have an expression for in terms of other things. Now, this is the equation that we essentially have to use to find the moment, but if you look at it closely, you'll notice that we also have another unknown, which is the shear force. So we have to deal with the shear force first. So to deal with the shear force, we have to look at the equation for the equation of motion in y. Now, if you look at the equation of motion in y, you'll notice that s is not the only unknown. We have another unknown we have to deal with, which is ay. Right, so that's the acceleration of the bar in this y direction, which is perpendicular to it. And to find that, we will have to use Euler's equation for acceleration. So I'm going to use Euler's equation for acceleration. So we use this. So the plan is we use theta double dot and theta dot to find ay. Once we find ay, we find the shear force. Once we find the shear force, we find the bending moment. Once we find an expression for the bending moment, we can differentiate it with respect to x. But you may also be aware that dm by dx should be the same as the shear force, but we'll do it anyway. And this is going to give us that location x star where the moment is maximum. Okay. So let's get to work. We have those, so that's fine. Now, in terms of ay, we have to apply Euler's equation. So basically, we're trying to find the acceleration of point C with respect to the origin and with respect to this tilted coordinate system. So if you imagine that I place this coordinate system of x and y at the origin, just to make things easier, this is what I'll have. So AC is going to be equal to the acceleration of the origin, which is going to be 0, plus alpha cross OC, and then minus omega squared times OC. Right, we said this is 0 because that's a point on the hinge which doesn't really go anywhere. So that's AC equals, we have IJK, then we have 0, 0 alpha, and then OC only has so OC only has an x component, which is relatively easy to find. So OC, so the length of OC is x plus L minus x over 2, which is L plus x over 2. So that's pretty straightforward. So L plus x over 2, and then 0 and 0. Minus, and this is going to be omega squared times L plus x over 2 multiplied by I. Okay, so let's find what AC turns out to be. So AC will equal, so it will only have a J component. So it will be J multiplied by alpha and then L plus X over 2. And then we have minus I times omega squared L plus X over 2. Now this part we can ignore because we won't need it. This is AX, or AX times I, and this is AY times J, and we said it's AY we need. Why do we need AY? Because that's what we require to find the shear force. Okay, so AY is going to be alpha L plus X over 2. So alpha is the same as theta double dot, L plus X over 2. So that is, therefore, we found it here. So that's minus 3g over 12 cosine theta. So minus 3g over 2L cosine theta, and then L plus X over 2. So the acceleration in the y direction of that section of the bar is minus 3g over 4L cosine theta times L plus X. Okay, so I shouldn't actually call it the acceleration of that whole bar. It's just the acceleration of the center of mass of that section of the bar. Right, so that's it. So now we can move some things around to find this value of S. So S is going to equal M over L. So let's actually write everything nicely without hopefully making any mistakes. So M over L, I need to drag this down here. Okay, so M over L times L minus X times the acceleration that we were looking for, which is this. So that's minus 3g over 4L cosine theta, or let me put the cosine theta at the end, like this. Okay, so that's the shear force, and then plus this part here. So that's plus, and we have M over L, L minus X, and this should be g cos theta again. So g cosine of theta. Okay, so now we just have to somehow bring this to a nicer and simpler form. So S as a function of X, basically, because X is our variable. If you think, well, theta is a variable of sorts, but we only care about how things change along the length of the bar. So S as a function of X is going to equal, and now we can factorize a couple of things. So we can factorize M over L, we can factorize an L minus X, a G, and a cosine theta, such that this second term is just going to be 1. And the first term is going to be minus, and we have 3 over 4, and this is L plus X over L. And I think that's it. So we can bring things to the same denominator. So we have M over L, L minus X, G cosine theta. So this becomes, so this turns into 4L minus 3L minus 3X, which is L minus 3X over 4L. Yeah, or let's actually put all the variables together so it looks a bit better. So S as a function of X is therefore equal to, so I'm going to combine the mg and cosine theta first. So we have mg cosine theta, and then we have L minus X times L minus 3X over 4L squared. So this already gives us a hint as to what the answer is, because we're looking for the place, we're looking for the center of percussion, remember. So we know that at the center of percussion, this is not center of pressure, it's center of percussion, you must have S equal to 0. And that happens twice according to this equation. So once for X is equal to L, which is obvious, right? Because at the top of the bar here, there's nothing. There's no shear force, there's no bending moment. The beam, the bar, the chimney is not attached to anything. But the other more interesting result is when X is equal, is when this is equal to 0. In other words, when X is equal to L over 3. Right? So this shows what we said at the beginning, that when X is equal to L over 3, this is where we have our center of percussion. So we're almost there. We just have to use this to prove that that's where the moment is the maximum. So let's do that. Now, the equation for the moment was somewhere up here, so I'm gonna bring it down. So the moment as a function of x is equal to, so this is the equation we have. And what I'll do here is I will move the moment to the right-hand side, and I will leave everything, I will put everything else on the left. So we have that moment is equal to minus s times L minus x over 2. And then we have minus 1 over 12. And we have m over L. Now this is L minus x times L minus x squared, so that's just L minus x cubed. And that is times theta double dot, which we know, so I'm going to substitute that straight away. So theta double dot was, so theta double dot is this one. So minus 3g over 12 cosine theta. So minus 3g over 2l cosine of theta. Okay, so mx is going to equal, actually we can simplify a few things, I believe, or at least one thing. So can cancel this 3 with this 12, and this is going, and this minus and this minus cancel out. So I'm going to write the second term first because that's positive. So that will be mg over, so we have 4 times 2, that's 8 L squared times L minus x cubed times cosine theta. And then we have minus, and now we just write the shear force. So the shear force is mg cosine theta. So mg cosine theta times that term with L minus x and L minus 3x. And I think it's over 4L, 4L squared even. So 4L squared, and this is then multiplied by L minus x over 2. So L minus x over 2. Okay, this is a relatively long expression, but we can factorize a few things and make it look slightly nicer. So first of all, we have mg over 8L squared in both terms, right? Because we have a 2 and we have a 4L squared, so this is 8L squared, and we have a cosine as well. And we have an L minus x squared in both terms. So now I'm going to open some square brackets. And from the first term, we have L minus x. And from the second term, we have L minus 3x, if I'm not mistaken. I think that's the only thing we have. So L minus x and L minus x, they go. So we're only left with L minus 3x, and that's it. So this is going to be mg over 8L squared times cosine theta L minus x squared. And this is multiplied with, so L minus x minus s minus L plus 3x is going to be just 2x like this. So that's the moment. So we have the moment, m as a function of x is, and we can also cancel out this 2 and this here. So we have mg over 4L squared. So mg over 4L squared times cosine of theta times x times L minus x squared. So now we should show that this bending moment is maximum at the center of percussion. So if we take the first derivative with respect to x, this is going to be mg over 4L squared cosine theta. That's a constant, so we can just leave it. And then this is, we can apply the product rule. Or we can put the x inside. I think that's probably easier. So let's do that. Let me write this first as L squared x minus 2lx squared and then plus x cubed, I believe. So, you know, this is the same as this. So now when we differentiate that, we get L squared minus 4lx and then plus 3x squared. Then we make this equal to 0 and we then try to solve for x. So this is essentially a quadratic. So we have 3x squared minus 4lx plus L squared equals 0. So we're going to do the usual method. We're going to find the discriminant. We're going to pray it's going to be a perfect square. And then we're going to find x. So this is going to be 16L squared minus 12L squared. And we have a perfect square, 4L squared. So x12 is going to be 4L plus or minus 2L over 6. The first solution is, I'll like take the negative one first. So 4L minus 12, that's 2L, 12 over 6, L over 3. X2 is going to be L. So this is not the one we care about, right? The one we care about is this. So we're pretty much done. So this tells us that the moment, there's a stationary point for the moment at x is equal to L over 3. And if you want, you can actually differentiate this again. It shouldn't be that hard to do. So if we do d squared m over dx squared, we're gonna find that this is equal to mg over 4L squared cosine of theta multiplied with, so here we have minus 4L in the brackets and then plus 6x. So if this is negative, then we're done. So because that's the only thing which controls the sign of the second derivative. So that's minus 4L plus 6 and x is L over 3. So that is minus 2L and it's negative, which means that x equals L over 3 corresponds to mx. And because it's at x equals L over 3, this also corresponds to the center of percussion of the bar, which we did somewhere here. Yes, this is it. So this is where the shear force cancels. This is where, you know, if you play tennis, if you hit the tennis ball with the center of percussion of the racket, you're not going to feel the impact, which is pretty amazing, I think. And that's also the point where the bending moment is the maximum. And that's the end of the question.